even though many species concepts make this assumption. For example, the biological species concept. When gene flow is taken into account, we have other possible options. For example, here we have 12,000 possible models, and these models can be categorized in isolation with migration, migration only, or mixed scenarios. And migration may have occurred between ancestral or present populations. When gene flow is taken into account in the system, first, species relationships are inferred, and then migration rates are estimated. But it is important to consider that if the topology estimated is incorrect, then further results such as migration rates or population sizes will be wrong. A potential solution to this problem is to co-estimate species relationships and gene flow. My study system here are Myotis bats. This is the most diverse genus of bats with more than 100 species, and there are morphological similarities between both the related species. Here I'm studying the western long-eared bats, which are mainly distributed in North America. These are the three species. I'm representing in blue Myotis ilii, in red Myotis botis, and in yellow Myotis pisanoides. Previous studies have used cytochrome B and cis-smuggler genes, and different methods are being applied, and the species relationships are still unresolved. My goal in this study is to infer a model that accurately depicts the evolutionary history of the western long-eared bats. I will present my methods and results together. First, we designed a set of capture probes for ultra-conserved elements specific to Myotis bats. A previous set of capture probes was designed to resolve phylogenetic and phylogeographic questions among vertebrates, but this set of capture probes is specific to Myotis bats. We used as a reference the genome of Myotis luciferus. We genotyped 80 samples, including as an outgroup Myotis luciferus, and this map represents our sampling. These loci, in average, have 39 segregating sites. First, we follow traditional approaches for species tree reconstructions, and we use Starbase, which is a popular software that uses the species coalescent model, but it is important to remember that Starbase ignores gene flow. Due to some computational problems handling the entire data set, we divided our loci in sets of 50 loci chosen at random, and we built 10 independent data sets. And then we used posterior predictive simulations to assess the fit of the multi-species coalescent model to each of these locus. These are our results with the Starbase. We recovered 3 different topologies, each one with a high support. This topology, where Myotis botis and Myotis pisanoides are sister species, was recovered 5 times. This topology, where Kii and Pisanoides are sister species, was recovered 2 times. And this topology, where Myotis ilii and botis are sister species, was recovered 3 times. When we assessed the fit of the multi-species coalescent model to each of the data sets, for example, here we notice that 0% of the loci had a good fit to the data. And overall, this was a common pattern. So we can conclude that the multi-species coalescent model, which ignores gene flow, is not a good assumption for this data set. It is usually thought that more data are the solution to resolve the species relationships, but here we have a big data set and we weren't even able to analyze it. So how did we address this problem? We developed Frapul. Frapul is a new software for phylogeographic model selection that can be used for species level questions. It is written in R, and here is the link. It is available and the papers are under review. Here I was able to analyze my entire data set, and I designed a set of 81 models that include all possible options with isolation, isolation with migration, and migration-only models. And to restrict the model space, we force migration to be symmetric. And then we use information theoretic approaches to calculate model probabilities. I'm going to explain how I am going to show my results because I will be using similar plots for the rest of my talk. Here, each column represents one model. Each row represents numbers of loci because we were also interested in knowing how the probability of each model changes as we upload data. And the color represents probability. Light yellow, low probability, and red, high probability, gradually increasing. These are our results for the 81 models. Here we have isolation-only models, and there we have migration-only models. I will explain this in detail. If gene flow were not important in this system, isolation-only models would have achieved a high support, but this is not the case. These two isolation with migration models achieved the highest probability. These two models out of 81 had the highest probabilities, which is 0.25 to 0.16. But these probabilities are not too high, so we were not happy with these results, and our next step was to fix these two topologies, and we generated a refined set of 320 models that include asymmetric migration. Here I have some examples of these models with these two topologies fixed with symmetric or asymmetric migration. And this time, a single model achieved a probability close to 1. In this graph, I want to show you the power of couple to detect the best model even with a small number of loci. Here in the x-axis, we have the number of loci, and in the y-axis, we have the model probabilities. And we require only 32 loci. And to achieve a probability close to 1, we required about 200 loci. A few years ago, this was a huge number, but by today's standards, it is relatively easy and affordable to collect this amount of information. As a matter of fact, we have more than that here. Okay, now we know that this model achieved a probability close to 1. It is an isolation with migration only, where Myotis evotis and Phylogenomics are sister species, and there is asymmetric migration from Guinea to Phylogenomics. However, this type of model can be explained by 3 evolutionary processes, and these are gene flow at early stages of divergence, constant gene flow, and secondary contact. So now we fix the timing of migration between these species, and we reanalyze our data in sets of loci. We included an isolation-only model just to rule out this option, be sure that we were not making the wrong assumption. And after analyzing 56 loci, we noticed that it was relatively difficult to identify between a model of speciation with gene flow and constant gene flow. But after 200 loci, it was evident that a model of gene flow at early stages of divergence achieved the highest probability. At this point, we know that gene flow is an important parameter that should be modeled in this system. But what is the cost of ignoring gene flow? I estimated the divergence times of these species, ignoring and considering gene flow, using 2 popular softwares. And we noticed that when gene flow is ignored, divergence times are underestimated 4 times. This result may have huge implications in studies of adaptive variations. As a complementary approach, we use environmental data to answer this question. An ecological niche tells us something about divergence with gene flow. And we used environmental data at different timescales, and we collected records from museums. In total, we analyzed more than 500 points. And we measured the niche overlapping between pairs of species. This measurement goes from 0 to 1, being 0 no overlap and 1 complete overlap. The niches of these pairs of species, which are not sister species, has remained relatively constant over time. But the niche of these 2 sister species, evotis and Phylogenomics, has decreased in overlapping. In the past, it was overlapped about 60%, and in the present, it is only overlapped by 20%. studies first infer species relationships and then estimate migration rates. Our new approach is to evaluate the fit of the ballistic model, which ignores inflow, and if we detect a poor fit to the data, then we use model selection tools to compare all possible scenarios at once. And the use of environmental data and museum records can be useful to confirm this type of phylogeographic hypothesis. As a conclusion, we know that the western long-haired bats are 3